Hello, in this video we are talking about Lenz's law, a fun little law that you can use if you need to determine the direction of an induced current. Let's get into it. We're going to be looking at a couple different situations where currents are induced, and often you're looking at something we might call an electromagnet. So let's talk about electromagnets first here. Remember the big idea for this unit and the link between electricity and magnetism? The link is motion. So we know now that the movement of charge is how you get a magnetic field. So when electric charge is moving, in other words, when there's a current flowing, you have a magnetic field. We have used this idea to design magnets with electricity, electromagnets. And what we do with these is we say, hey, we can get a strong magnet if we run some current. So we take a whole bunch of wire and make a whole bunch of loops of wire, coils of wire. So you get a bunch of wire, many loops of it, and you run a lot of current through it. You're going to get a strong magnetic field. So these electromagnets, junkyard magnet is one you might have in your brain. That's what it is. All that's happening in this here magnet thing is there's a whole bunch of wire spooled around inside of here, and you run a ton of current through it, so you get a really strong magnetic field. The nice thing it's powered by electricity, so you turn the circuit on, you run some current, and the magnet's working. You pick up your car or what have you, you play the claw game and bring it over to where you want it to go, and then you turn off the circuit, and the magnetic field goes away, and you can drop the stuff. So that's the idea of an electromagnet. And this whole idea of coils of wire being used for magnetic field stuff comes up all over the place in this unit. There is a rule for the direction of the magnetic field that you make with this kind of thing. So I'm calling this right-hand rule number 3. It is very much like what I called right-hand rule number 2, just the backwards version. In this case, now we're going to have current doing like circular or, curly kind of stuff, and the magnetic field is going to be more or less straight. Here's what these are going to look like then. If you have an electromagnet, or sometimes you're going to see the word solenoid. Solenoid is a similar idea. We could call either of these things a solenoid, which is, again, just a coil of wire that we use to run current through it and make magnetic fields. We use these in circuits and little electric devices all the time. All right, so a coil of wire creating a magnetic field is what we're talking about. What you would do to determine the direction, like which side of your little electromagnet or solenoid is the North Pole side, you take your hand and kind of make the thumbs up sort of arrangement so that your fingers, your four fingers are kind of like curling around your thumb, if you picture it that way. If you set it up so that your fingers are curling in the direction the current is flowing, which you can think of as like clockwise or counterclockwise from wherever you're looking, then your thumb will point towards the North Pole end. So for this one on the left here, you would want to take your fingers and point kind of with your palm facing towards the screen, your fingers pointing down, because the idea is here we're seeing the current kind of comes in, and your fingers would like curl kind of into the screen and back on themselves and then around like this and like this. So the direction, like the way these are drawn, is going to matter. You're going to have to like interpret these to know that this is going like from the bottom, it's going into the screen, and then it comes up and around, and out of the top, it's coming out of the screen. So your palm is like facing you, your fingers are curling towards you on your right hand, and your thumb is pointing to the right. This shows us that the magnetic field is to the right. In other words, your thumb points to the North Pole side of your little electromagnet. And one of the big ideas here with this electromagnet or solenoid is that inside of the loops, you have a pretty much uniform, nice, straight magnetic field. So we have a uniform B field inside of your electromagnet slash solenoid, similar to what we saw a little bit with their parallel plate capacitors, two charged to a plus and a minus plate. You get a nice uniform electric field in between. Okay, so you use that to determine like which way a magnetic field is going when there's current moving in a loopy kind of way. Well, we do that because current is moving in a loopy kind of way all the time when we like generate electricity and induce voltages and currents. So we're going to use this a lot when we learn this Lenz's law thing. Okay, a good way to think about this Lenz's law idea is going to be energy. Of course, energy, the most important thing maybe in physics, the thing that comes up over and over again. Conservation of energy, maybe the most fundamental rule we have in science. And the idea with this is picture what's happening when we talk about this crazy induced EMF stuff. What we're saying is you can like move a magnet near a coil of wire and you magically get electricity flowing. It works. We can do it. We can test it. But we should be thinking about that means we're generating energy somehow. We use this to generate all of the electricity that we like use, more or less. So where does that energy come from? Take a moment and think about this. If you're moving a magnet and inducing a EMF, where is that energy actually coming from, and what does that mean for the magnet? What's the transformation? Well, I think it's the kinetic energy of the magnet. Remember, you need motion for this to happen. So once the magnet is moving, it's got some kinetic energy. Maybe that is the energy that is sort of being used up to create electrical energy. Now think about if we're transforming kinetic energy into electrical energy, what would that look like? Well, that means the magnet would slow down, or maybe certainly not speed up. We're going to take kinetic energy away from the magnet to make this electricity. So there's a fun experiment you can do where you take a strong magnet and drop it through a tube of like a copper tube or any kind of like conductor. So here it looks like a magic trick. There's a really strong giant magnet there inside this little cylinder of copper. As the magnet moves, there is a current induced in that. This is basically one big loop of wire. You can almost think of it as just a loop of metal, and current will flow around. Eddy currents, we sometimes call them, will flow around this piece of metal. So if the current is happening, that energy must be coming from somewhere, and it's two ways to think of it. Most officially, it's really coming from gravitational potential energy. So that magnet kind of starts to fall, and instead of what normally happens, instead of that potential energy turning into kinetic energy and the thing accelerating as it falls, that potential energy is like immediately turning into electrical energy rather than kinetic. So because you're making this electrical energy, you don't speed up. All right, so conservation of energy is what's happening. Another way to picture this is there's some resistive force acting on that magnet as it falls, and the work being done involving this resistive force is going to translate to the electrical energy we're making in the in the coil here, in the copper here. So let's get an official rule kind of out of this. So far, we talked about how you find the size of an induced EMF, and that was Faraday's law. Faraday's law only gives the size. Lenz's law gives the direction. And here is Lenz's law. Lenz's law says the direction of your induced current is such that it will oppose the change that created the current. All of this stuff comes from a change in magnetic field, a change in magnetic flux officially. So Lenz's law says whatever changing flux creates this EMF, the induced current is going to oppose that change. So we'll have to look at what this means, because that's a crazy, kind of confusing statement. All right, remember this equation in the data booklet is Faraday's law, and here's a good way to think of Lenz's law. Lenz's law is essentially this negative sign. The negative sign is a little notation that we use to say the induced EMF is always going to oppose the change in flux. It's kind of strange because typically you treat this equation like you drop the negative sign to find the size of the number, and the negative sign is sort of a reminder to do some crazy right-hand rule stuff and figure out what your direction is going to be. It means the direction opposes the change in flux. But because of our 3D stuff, this gets a little wacky. Here's another good way to think of this when you're doing Lenz's law problems. This is usually the best way to do a straight up problem with Lenz's law because they're pretty tricky. There's going to be a resistive force. That should be your first kind of point when you're trying to figure stuff out here. There's going to be a resistive force. So that right-hand rule that we did is going to be helpful because you can think about North Pole, South Pole, and attract, repel is often the easiest way to do these if you can think of, okay, there's a resistive force. So like, is there attraction or repelling happening in which way? And then you set up your right-hand rule. So for Lenz's law, try to start with the resistive force if you can. We're going to look at some examples in a second so you see what I'm talking about. And remember, Lenz's law is all about conservation of energy. This is something the IBU will often ask you to talk about too, and essentially say, explain what's going on with Lenz's law. The most important thing to say is conservation of energy. All right, that's why there's a resistive force. You're turning energy from the magnet, mechanical energy, kinetic energy, something like that, into electrical energy. So let's try a few. Here's the types of problems you'll see. We're going to look at all kinds of situations. Okay, so let's start with our classic example where I have a coil of wire and a magnet, and I'm going to move the magnet. The magnet, I can move it, you know, one way or the other. I can move the magnet like this. I can move the magnet like this. And we saw from some experiments that that is going to create an induced current. Current will flow in my little loop of wire here. And this is a little, supposed to be, it's an ammeter. It's a galvanometer, which measures really small currents. But this is a little thing that's going to measure the current. So we want to decide in this question, which way will the current flow? The current is either going to flow from X to Y, like this way, or from Y to X, like this way. So we're going to try to figure that out. All right, let's say first the magnet moves right. So the magnet comes in like this. The whole north-south thing is going to be important here. So the north side of the magnet is here. There's a few ways you can think of this, but again, the best thing to do is to think, okay, how am I going to get a resistive force? Because I know there's conservation of energy. Nothing's free. You can't get free energy. I'm going to be creating some electricity that has to cost me something, which means you have to do work to really move the magnet this way in order for that to generate some current. So there's going to be a resistive force. Here's how to think of it. You're going to have a little electromagnet over here, and on this magnet, one end is going to be north, one end is going to be south. Which way do you think it should go if there's going to be a resistive force? Which side of this, electromagnet over here with point P in the middle, which side of this is going to be north, which side is going to be south? Okay, well, to resist this motion, the left side would be north here, the right side would be south. This would make it so that when the magnet's moving to the right, it's being repelled by this magnet that we're making. Okay, we're like making a magnet that repels us. So we want the north side of the electromagnet to be over here. That's what Lenz's law says should happen. There should be a resistive force that goes along with this current that we're inducing. So now you can reverse engineer your right-hand rule. If I know that the north side of my electromagnet is going to be to the left, I'm going to point my thumb to the left, and my fingers are curling to go like into the screen or into your page at the top of the loop and come out at the bottom. So this current is going to go over the top then. So if I curl my fingers like in this kind of direction over the top and then kind of out and under at the bottom, that's the direction of the current that's going to give me a right-hand rule where my thumb points this way, and that means my north pole is this way. So if the current is flowing this way in this little coil, there's a north magnetic pole over here, which will resist the change. Now I want to picture like how this is drawn matter. So it comes up and around and then comes down like this. So the current is flowing like this way. And so the current is flowing from Y to X. Okay, so north's going to repel north as it comes in, which the way to make this side the north pole is for the current to curl in that kind of direction. All right, let's try the next one and see if this is starting to make any sense at all. Okay, now let's say the magnet moves to the left. We know this will still induce a current. You'll still get some, electricity happening. But what's going to happen? You might have a guess based on what we saw when you did some experiments like this that perhaps things might flip. Let's take a look and see if it makes sense why. Now this magnet's moving away. How could this one oppose that change? Or in other words, how could there be a resistive force? Well, if this magnet's moving away, the resistive force acting on the magnet would be this way. Yeah, there'd be a resistive force is always opposite your velocity. That's the definition of a resistive force. So if this thing's moving to the left, it must feel a force to the right. Again, in order for it to be generating some electricity. Well, for there to be a force to the right, this would have to be a south pole. It's attracting the magnet. Okay, Lenz's law says all this stuff is like very fickle. So the magnet gets pulled away, and it's like, wait, no, don't go. I don't like that. But then you move the magnet towards it. It's like, no, don't come any closer. All right, so it hates change. That's all it is. Nature hates change. And if things are changing, it's going to try to oppose that change. The magnet moves away, it tries to slow it down. Magnet comes towards it, it tries to slow it down. To slow it down this way, I need a south pole here and a north pole here. Let's point our thumb towards that north pole. Now I think my fingers are coming out of the top of this, out of the screen, like towards the top of this loop and going into the screen towards the bottom of this loop, which means when I point my thumb on my right hand towards this side, my thumb's pointing this way. Then my fingers curl around like so. They kind of come up and over and then go like this, up and over and go like this. So my current is indeed going to flow the opposite way here from X to Y. All right, so there you go. That's how you do it with a resistive force, which is a great way to do it. Let's try again now. Okay, pause the video and you try this one. We flipped our magnet around. We're going to do the same situation. We're going to move that magnet to the right, move that magnet to the left. See if you can figure out which way does the current flow, X to Y or Y to X in these two situations. Give it a try. All right, here's what you should get. If the magnet moves to the right, then to oppose that change, I need a south pole here. I need to repel that magnet. It's coming towards this. We're the coil, okay? So the magnet's coming towards us. We hate change. We say, no, get away. We're going to repel it. So we're going to do south to south so that they repel, meaning I point my thumb towards the right side here, the north pole. My fingers will curl like so, up and over. And that means current here is going to flow X to Y. All right. Then the opposite will be true if it's moving this way. If the magnet's moving this way, then to oppose that change, this side has to be the north pole. It's moving away. We say, no, don't go. We change our minds. And we try to pull it back. To pull it, I need north and south so that they attract. And now I'm going to point my thumb this way towards the north end to figure out this part B. And my fingers are now, when I do that, going to curl up and over and go into the page at the top and come out of the page at the bottom. So my fingers are kind of curling in this sort of 3D way, meaning the current in this case flows Y to X. All right, these take some practice for sure, but there's a couple examples of how you do them with resistive forces. Some other ways to think of this, magnet moving towards a coil situation, which you see all the time. If this is better for your brain, you can think about what's going on with the B field. Pretend again, you're the coil, you're the loop of wire here. There's a magnet coming towards you, and the magnet itself has a magnetic field this way, and it's, in this case, getting stronger. So you, the loop, as this magnet moves towards you with its north pole kind of facing you, you see a magnetic field going, towards the right-ish in this scenario and getting stronger. How will you oppose that change? Well, you will create a magnetic field, an induced magnetic field, we say, to oppose that change. So there's an increasing B to the right. We're going to create a B to the left to oppose it. And now same deal, you point your thumb in the direction of the induced magnetic field to find the direction of the induced current. And if your thumb is pointing this way, your fingers will curl kind of this way. Yeah. In this case over here, if we want to think of it in terms of the fields instead, I have a magnetic field pointing this way to the left now that's getting stronger because now the south pole is facing it. So I got a leftwards magnetic field getting stronger. How would you oppose that change? Well, you would create a magnetic field to the right. So you would have an induced magnetic field to the right, which would give you current flowing this way according to our right-hand rule. All right, so there you go. Here's one other example, which is like the double negative one. That's a tricky one. In this case now, if I were to take like this magnet and move it away, that's what we're kind of looking at here. Okay, in this case, the magnet's magnetic field pointing to the left is what the loop sees, and if the magnet's moving away, it sees that field decreasing. Yeah, so now instead of the North Pole coming in, the North Pole is going out. The North Pole is going out. We see the B going through the loop in a certain direction. It's decreasing. How would you oppose that change? Well, you would create an induced field to make up for what you're losing. So it'd be in the same direction. So it doesn't mean the two fields are going to be in the different directions. It means you're going to oppose the change. That's the rule. So the field that was to the left is decreasing, and you say, no, I liked that. I hate change. Let's make some more field to the left to make up for what I'm losing. You get induced field like this, and if you do your right-hand rule, oh, sorry, I drew that backwards. We're going to get current kind of flowing this way. So my thumb is pointing to the left. My right hand's fingers are curling into the screen at the top and out of the screen at the bottom. All right, easy, right? Super easy. Okay, you'll have to practice these. Let's look at some more examples because there's lots of other ways Lenz's law can come up. Something that you have to consider all the time when you're doing circuit stuff where you're going to have pieces of circuits turning on and off with switches. Think about this. Let's say I have a little circuit with a coil of wire, and nearby is another coil of wire, just for fun. What's going to happen when I close this circuit? Picture what's going to happen. Current is going to start to flow, right? At this point in time, current is 0. So there's no current. And then as soon as we flip the switch, current is going to begin to flow. Yeah, so current will, after we flip the switch, flow and go through the wire and flow all the way around. And I'm going to have some current moving through a loop, which means there's going to be a magnetic field in a certain direction. The current is going to go, if we were to track like current over time, the current starts at 0, and then eventually and probably pretty quickly is going to hit some certain amount of current, but nothing in real life happens instantaneously, so it's going to take some time like for the current to get up to whatever value it's going to reach. In this case, you have a change in current, which means whatever field you make, let's say we make a magnetic field that's like pointing this way. So this is the field that's going to appear. But at the beginning, there's no field there. So what's going to happen? Once we turn on the switch, this magnetic field appears. We start to make that field. Right as the switch turns on, this loop is going to see a magnetic field appear. It's going to experience a change in flux. Right now, the flux is 0 for this loop. In the beginning, before this field appears, when the current is still 0. And then there is some flux, right? And there's some flux like this way. There's a magnetic field this way. It wants to oppose that change, so it's going to create an induced EMF to create an induced magnetic field that will oppose the change that created it. But it's going to go, no, I don't like that. And it's going to generate its own little current flowing in this case, opposite direction and make a field that opposes that change. All right, that would be the first thing that happens when you turn the circuit on. But remember, this happens when there's a change in flux. after a probably very short amount of time, you're going to hit this current, and the current is eventually going to hit some constant value. So make a prediction. What do you think will happen then after a few seconds? What will happen? What would we see maybe on this needle if this is measuring current in our second loop? If you get 0, that's the answer. After some time, the current has stabilized to some constant value. So you still have a magnetic field here, probably a strong magnetic field here, but it's constant. It's no longer increasing from like 0 to whatever. Now it's reached whatever. And since it's a constant magnetic field, this doesn't care at all. There's going to be no EMF because there's no change in flux anymore. So it doesn't matter at all that whether there is or isn't a magnetic field through the coil. All that matters is the magnetic field changing. That's the only time you get a reading, is if the magnetic field is changing. So a no magnetic field through the coil and a constant magnetic field through the coil have the same effect, which is none. All right, you don't get any induction. Last step, let's turn off the circuit. We're going to open this switch now to turn off the circuit. So we're going to stop the current. Take one final guess what's going to happen to our little meter here. Well, it's going to go in the opposite direction. Okay, so again, think about how you're going to pose the change. We still have this, the split second we open the switch, there's a field to the right. And as we open the switch, that's going to very quickly drop to 0 because the current stops. But again, nothing like instantaneously drops to 0. In real life, it's going to take a fraction of a fraction of a fraction of a second for all that current to like slowly stop, or quickly stop, we should say. So the magnetic field that was here quickly decreases down to 0. Well, how would you oppose that change? If you were this second loop, you would create your own induced magnetic field this way. So current would flow the opposite direction that it did before. So you're going to measure a current like a negative current where you measured a positive current before, let's say, or the other way around. Right? So you're always creating an induced magnetic field to oppose the change. If the strength of the field through the loop is changing, or if the flux is changing in any other way, you are going to be creating your own little induced magnetic field to oppose that change. That's the key thing to remember for all of these. Try your best to start with. We're going to oppose the change. Okay, there's even more fun ones. Let's try another one like this. Here's another common problem that we physics teachers love. It's so fun and exciting. Look at this. We get ourselves a little loop of wire in a magnetic field, and we take the whole loop of wire and we move it. So we're going to like move that loop of wire, like a nice little square loop here. We're going to move it this way and pull it out of the field. So there's like a boundary here where there is a magnetic field here, but the idea is like there's no magnetic field right outside of it. So make a prediction. What do you think is going to happen in this situation? As that loop leaves the field, there will be an induced EMF because there is a changing flux situation. Think about how. So what's going to happen? Which way is an induced current going to flow in this loop? Clockwise or counterclockwise would be your options. If you can try to pause and apply this Lenz's law idea and figure it out. Okay, here would be the idea. Currently, at this split second freeze frame in time, inside of the loop, there is a flux. There's a whole bunch of spaghetti pointing through the loop like this way, like into the screen. So the magnetic field currently through the loop is pointing in. There's a certain amount of flux inwards. What is happening to the size of that flux as the loop leaves the field? Well, I think it's going to be decreasing. As this loop moves out, it's eventually going to be at some point where it's got, just a little bit of that magnetic field in it, and then most of it, like there's no magnetic field. So the flux is decreasing. To oppose that change, then, which way would the loop create its own induced B field? well, it would create it into the page as well to make up for what it's losing. It's trying to keep a large amount of flux into the page just because that's what's happening already, and nature hates change. So it's going to try to oppose losing some X's, losing some B fields into the page by making up for them, making some of its own. Now, the last step is if it creates a magnetic field into the screen, which way is the current? We're going to use our right hand rule. Point your thumb into the screen. So your thumb should, touch your piece of paper. And then your fingers, if I'm looking from, onto my piece of paper, they're curling clockwise. So the current here would be clockwise. So current's going to flow like this, like this, like this, like this, in order to create the magnetic field that will oppose the change that created it. Okay. All right. Those are some good classic examples. Like all of those have shown up multiple times on IB exams. So they're very good to practice as you work on these. Try practicing some Lenz's law. They're tricky. It's one of the trickiest things in this unit. So do some practice with Lenz's law and start to get the hang of it. Oppose the change is the key thing to remember. Last little piece of knowledge to know here, related to the second to last example we just did. When stuff turns on and off in circuits, you have change in current. It happens very quickly, but you do have a change in current. And whenever that happens, there's a change in flux, so some kind of EMF is going to be induced. There is something called self-induction. So if you have yourself a little loop of wire and you turn on the current, when the current is increasing, within the wire itself, it's making its own, so the increase in current is making a magnetic field that, kind of hard to tell which way this thing is drawn, but let's just say it's making a magnetic field this way. That's like the existing B that it's making, that's increasing as it turns on. Well, that means the wire itself is going to also, like on top of, superimposed on its own signal, is going to create this little back EMF, we call it sometimes, a self-induced back EMF. It creates a little, much smaller than the main effect, but it creates this little magnetic field opposing its own change. Same deal. If you turn the circuit off then and the current is going this way and decreasing, you get an induced EMF that tries to counteract that. So if you turn this thing off and your field that's to the right suddenly starts to decrease, the coil itself will also, for a split second, create its own little induced magnetic field to the right. Again, picture this as like two different currents almost superimposed on each other, kind of like waves. They'll add together math-wise. So this is called self-induction, and it is something we use in circuits a lot. Inductors are pieces of circuits. Again, we don't really talk about it much in IB physics because they're usually very much related to AC circuits. But inductors can help prevent spikes in voltage or rapid changes in current because of this. So last thing here is a nice little graph to maybe help picture this a little bit. Okay, if you had a circuit where you have like, a battery and a resistor or something, you turn the circuit on, math-wise, you go from like 0 potential difference to, 9 volts of potential difference, like immediately, and then all the way down to 9 volts. So you would get a crazy fast spike in voltage, a like infinitely fast spike in current, which in real life, is not great for electrical components. So what happens if you put a little coil in there, you get this back EMF. And as the change is happening, there's a very quick EMF that opposes that change. But as soon as you hit some stable voltage, it quickly drops to no EMF because this is the part that's opposing the change. So when change is happening, the back EMF is really big. At all other points, it's really small. So whenever there's a change, this kind of counteracts that change and smooths things out. So if we kind of ignore all of this back EMF stuff and we just go to good old like, oh, V equals IR, and it's just going to all happen immediately, the math would say this would happen, the top curve. In real life, this is what happens because of this back EMF stuff. So as you turn the circuit on, it doesn't immediately jump up because it opposes its own change. And so the current more gradually comes up and reaches this steady value. And then when you turn the circuit off, rather than immediately dropping to zero, the back EMF will let it slowly drop to zero. Again, we say slowly, this is all happening fractions of a second usually. But that's the idea, is the self-induction will smooth out these changes in voltage and current that happen, especially if you have like a coil of wire, like an inductor like this. All right. So again, we don't get much deeper into it than that because we don't really do much with inductors, AC circuits, or anything like that. But the IB wants you to know self-induction is a thing. So there you go. Self-induction is a thing. All right. That's Lenz's law for you. Do some practice. Try some right-hand rules. Try to see some of these different examples of how you can oppose a change in magnetic flux, and see what you come up with. All right. Have fun.